Hello, my name is Cooper McAllister, and this is my presentation on historical engineering. So the first time period of historical engineering is classical antiquity, and for this time period I chose to study the Egyptian obelisks. So these are basically big pieces of stone, and they're normally used to honor a particular god or a king, and they included inscriptions describing that ruler's acts. They're known to have been erected as early as the 4th dynasty. And the interesting thing about these obelisks, and the reason I chose to study them, is because we actually don't really know how they were raised. So we do know that they were carved out of a big piece of stone. It was normally red granite. That took about 7 months, and then they were transported to their destination. However, we don't know how they were raised to the upright position. There's a couple different theories, like maybe they used a funnel-shaped hole filled with sand, and then somehow shoveled the sand out of the hole while the obelisk was raised into position. Another scientist has devised a system of like kites and pulleys and supports to pull the obelisk up. So those are some different theories, but we really don't know, and that's what makes it really interesting to know how these Egyptians, with their ancient technology, managed to raise these huge pieces of stone. So a couple of different examples of the obelisks are some at the Temple of Heliopolis. These are the earliest surviving obelisks, and then a pair of obelisks at Karnak, which were erected by Thutmose I. Alright, so the second time period is the medieval time period, and for this time period I chose to study mechanical clocks. So the Verge escapement was what kind of began the development of mechanical clocks. That was around 13 AD, and clocks were first used in monasteries. They were normally used to ring bells that would signal monks as a call to prayer or other duties like cleaning and stuff like that. And the clock I have shown here is from the Salisbury Cathedral, dates to about 1386. So here I have a picture of the Verge escapement, and it has this toothed wheel that engages these paddles as it turns, and these paddles are connected to some sort of weights that provide inertia so that the paddles move at a certain speed, which slows down the rotation of the escape wheel as it's turned by or propelled by some sort of weights. And other than the escapement, the rest of the Salisbury clock consists of a large iron frame. It was actually held together by mortise and tenon joints, which is what they would use for woodworking because bolts and screws hadn't been invented yet. And this mechanism is separated into two main sections. There's the going train, which keeps the time, and the striking train, which strikes the bell every hour. Alright, so the next time period is the Scientific Revolution, and for this time period I chose to study the first photograph. So it's titled The View from the Window at Le Gras. It was taken in 1826 by this French guy. We'll just call him Joseph because I have absolutely no idea how to pronounce his last names. And he used a camera obscura and the heliograph process. So a camera obscura is basically a box with a small hole in the side, and that hole causes the light rays that come in to be projected and form an image on the back wall. And then the heliograph process consists of a polished pewter plate coated with light-sensitive bitumen, which is dissolved in lavender oil, and this plate was placed at the back of the camera obscura, and then it would be exposed to light for several days. Once it was done, it produced an image on the plate. And Joseph later improved on this process to invent the daguerreotype process, and that was what led to basically modern film photography. Alright, the next time period is the Industrial Revolution, and I chose to study the power loom. So it was first completed by Edmund Cartwright in 1785 in England, and then Francis Cabot Lowell actually stole that design and brought it over to Massachusetts in 1814. And these looms still required some sort of human intervention. The first fully automatic loom that didn't require any human operation was designed in 1834 by James Bullough and William Kenworthy. These power looms effectively increased a worker's output by 16 times or more, since you only needed a couple of workers to oversee an entire warehouse of looms. So these looms basically worked the same as manual hand looms, and they contained power trains that ran all the same components, so things like the warp beam, heddles, harnesses, shuttle, reed, and take-up roll. And then those fully automatic looms I talked about, those also had a system for changing the shuttle once it ran out of thread. And these looms also used the design of the flying shuttle that was patented by John Kay in 1733, and so obviously that played a big role in making these power looms possible. And they also used a great deal of complex engineering. So pulleys, belts, gears, levers, and springs, all sorts of mechanical engineering. So for the second industrial revolution, I chose to study the airplane, and the first flight of the airplane was made by Orville Wright on December 17th, 1903. I'm a student pilot, so airplanes are obviously really cool to me. It's hard for me to not include them wherever possible. And not only are the airplanes themselves cool, but the engineering design process behind them is also really interesting. So the Wright brothers, were involved in a great deal of research before they actually made the airplane, and so they did things like researched previous attempts at making aircrafts, the flight of birds, and they built their own wind tunnel to test different airfoils. And they also used the knowledge they had gained from building and selling bicycles for several years to build their airplane, so a lot of that mechanical knowledge. And then their machinist, Charles Taylor, also helped them particularly build their engines. So the first thing the Wright brothers did after all that research was they built a series of unpowered gliders to refine their design and make sure that they really understood how flight works before they added a motor. And then once they were ready for that, they added the motor. It was basically just an engine in the middle and then had some belts running to the propellers. Their propellers were actually a big innovation because the Wright brothers were the first to view the propeller as a wing in motion. And so that's really the right way to think about it. It's not like a screw or anything like that. That was how some people were previously thinking about it. But they thought of it as a wing in motion, and that really helped them to make more efficient propellers. And their propellers were almost as efficient as modern propellers, which is really impressive for the very first propellers. So after that first monumental flight that the Wright brothers had that everyone knows about, they actually didn't stop there. They developed the aircraft a lot more until they could stay aloft for more than 30 minutes at a time, and they could perform all sorts of turns and climbs and descents, all basic aerial maneuvers. And then in 1909, the Army ordered a modified version of the Wright brothers flyer to use for aerial observation. Obviously that played a big role in World War I, and then the airplane played an even bigger role in World War II with the development of bigger planes, bomber planes, fighter planes, all that. Alright, the last time period of historical engineering is the information age, and for this I chose to study the Mars sky crane. So this is the system that was used to land both the Curiosity rover and Perseverance rover, and it provides what engineers have determined to be the only workable solution to the problem of landing a big car-sized rover on Mars. It allows the landing target to be made much more precise so they can land in much smaller areas, such as Jezero Crater, where the Perseverance rover landed. And that's actually a pretty small area, but they wanted to do some specific scientific research in that area, and so the Mars Sky Crane let them do that. So both missions that used the Sky Crane cost around $2.5 billion. Obviously not all of that went into the Sky Crane, but pretty expensive for the entire mission. So there's this thing called the 7 minutes of terror, and that is the time between entry into Mars' atmosphere and when the rover lands. And so at first, the rover and the Sky Crane are in some sort of shell, and that falls under a parachute. Then that parachute detaches, the shell comes off, and then the Sky Crane turns on its rocket motors to slow its descent until it hovers over the surface. Then the rover is lowered on cables, and then once the rover is safely on the ground, the Sky Crane detaches, those cables fall away, and then the Sky Crane uses the last of its fuel to fly away and basically crash itself somewhere on Mars. And so the Sky Crane was the result of a very lengthy development process that was focused on solving this big problem of landing a car-sized rover safely, like I talked about. And so it was a very multifaceted project and involves elements from almost every aspect of engineering, so things like mechanical and electrical engineering, aeronautical engineering, of course, and even stuff like chemical engineering for those fuel systems and stuff. So a lot of different things that went into that project. Alright, so that concludes my presentation on historical engineering. I hope you enjoyed learning about some of the things I researched.